భోజనం చేసారు లేదా ఇంకా స్టార్ట్ అవ్వదు సార్
ఎక్కడ పడి మీ నెట్ రాలేదు కదా ఇక్కడే బాగుందా కొంచెం నొక్కా కొంచెం వాళ్ళు చంపేసి అన్ని కదా కాంగ్రెస్ వాళ్ళు అసలు ప్యాలెట్ చాలా బాగున్నా
చంపేనా చేస్తున్నారో తెలియదని చెప్పారు
ఎవరు చంపేసుకున్నాడు అది ఉండాలంట అయినా ఆవిడ ఊళ్ళో కేరళలో వచ్చిందంటే ఎంపీ కూర్చోండి అలా ఆవిడంటే బాగుంటుంది ఎంపీ లెవెల్లో ఏమైనా చూసినట్టు మంచి సంబంధం నేను అలాగే పడుకోబెట్టుకుంటున్నాను
లేదా సార్ స్కూల్ కూర్చున్నాం దానికి సార్ రావాలి, సార్ పాస్పోర్ట్ పెట్టి చెప్పి చేయాలి. సీనియర్ ఏదో ఒకటి చేస్తాను మళ్ళీ ఏం చేశారు చెప్పలేదు. ఇప్పుడు వాటర్ మరీ ఉంటుంది. ఎక్కువ వెళ్ళిపోతాయి. స్టార్ట్ అయిందా? వాటర్కి మళ్ళీ వెళ్తుంది. ఆకాశం వచ్చి లేదని మొత్తం పడిపోయి స్టార్ట్ చేస్తే
అంటే పై హ్యాండ్ క్లిక్ చేసినప్పుడు అది ఓపెన్ చేసినప్పుడు రాదు.
మన వాళ్ళు ఇచ్చేస్తారు కదండి.
రమ్మని చెప్పాను భాస్కర్ గారికి ఫోన్ చేసి. ఎవరైనా నేర్పేస్తున్నారు, ఎవరైనా సహకారం అది
కాదు. నువ్వు అజయ్ గారు ఎవరితో ఉంటే అక్కడ డ్రైవర్ ఉంటే అందరికీ నేర్పించుకుంటాను. అట్లా ఆ సెంటర్లోనే కమ్యూనికేట్ సెంటర్ ఉందని ఆశ్రమ పెట్టుకుంటుంది పక్కన పెట్టారు.
మామూలు ట్రైనింగ్ స్కూల్ ఎంత తీసుకుంటారండి?
3,000 మళ్ళీ కిలోమీటర్లు లెక్క వెళ్తారు. రోజు 14 కిలోమీటర్లు అంటే రోజు గంటగా నేర్చుకుంటాను. రోజు 14 కిలోమీటర్లు అంటే మీకు ఎక్కడి నుంచి ఆ స్పీడింగ్ కొడిసారంటే పావుంటే తిప్పేస్తాడు.
మళ్ళా క్లైంట్ ఆన్లైన్ కదా అది కూడా
so most of the by using theory we should not use any constraints on the placement. So whatever constraints we want to use, we have to use only a master node. So and as this period and generally this
మనం చేసే
and on RV it is similar to theory. Here also there is to have a master and a
అదే ఏమో పర్మిషన్ ఇస్తే మళ్ళీ ఏమన్నా
the
వచ్చేస్తాను
only difference between
పర్మిషన్ లేకపోతే
seed and harvesting is in seed the degrees of freedom for master is independent. Whereas here master degrees of freedom are dependent. That means they are dependent on slave mode. So basically slave mode
ఏదో ఈరోజు సింపుల్ చేయడం కదండి
so in seed master mode is very here slave mode
అది రాయాల్సిన వచ్చేస్తుంది చెక్ రాయాల్సింది
that is a major difference between theory and practice. So
చెక్ రాయాల్సిన ఆల్రెడీ ఎప్పుడు స్టార్ట్ అయింది కదా మళ్ళీ వచ్చేస్తుంది
average of slave.
ఆరు పడిపోతారు
So basically the function of the is the average of
చెక్ రాయాల్సింది ఇంకా ఆల్రెడీ
and one of the important thing is in my theory we can apply loads as well as in market we can apply only no so if you try to constrain most of the here is again there is a conflict happening. So if you have
ఎట్లా దగ్గర చేసుకుంటూ అన్ని తెలుసుకుంటూ అనే అవుతుంది
so process comments and mark of master
సో
can be so when you apply both
అలాగే చదవగలిగి రెండు విధాలు నచ్చాలి నా ఆసక్తి నచ్చుతుంది
distributed
నిజంగా
through all the let us look at one example. So here we have taken a case here, theoretical case. These are the geometry type of case. This is the length of the case, and the diameter of the case is so this case is so we want to analyze this case.
అలా జాగ్రత్తపోతున్నాను స్ట్రెస్ పడతాను ఎంత స్ట్రెస్ పడితే ఈ ఆకలితాయి ఇలా విరిగిపోతాయి అదే స్టడీ అయిన తర్వాత అవుతుంది అదే మెటీరియల్ స్ట్రెస్
other points are good, but for this analysis, we need to take these 4 points. So one is modeling study. So we will use 3D models or shell models. Now, study one thing. Second thing is what is the and goals. So these are the 4 things we need to use. So on middle probability, we have taken a series of middle probability. And we will discuss on modeling strategy. So coming to modeling strategy, let us look into the whether this filter case it's a surface type of filter. You can see here this filter is subject to addition. Okay. So this is perfectly determined. So now let us see whether this geometry can be modeled at center. If it is right or not. So coming to axiometry related information, a special method that public can consider into correlation with reasonable assumption about variation of unknown parameters in the third dimension. So if you take any 3D three-dimensional problem, we can make it two-dimensional problem. If we can make very good assumption in the third dimension. So, for example, in this case, if you take this cross section, so along third direction, if you make suitable assumption, then you can take it as a 2D graph. Similarly, we have plane stress and plane stress problem. We have very assumptions and we can take it as a 2D dimension problem. 2D models such as plane strain, plane stress, plane strain, and plane so in our model, the current model is a axisymmetric problem. Geometry is axisymmetric. Then our consider it as a axisymmetric. So some of the points related relevant to the function and coding is in same line. So geometry is in constant, but loading should be one plane. Loading is this model can work in for axisymmetric cases, and we will develop only stresses or non-resistance and no stress direction through. So when you try to assess thickness ratio or thickness ratio is so here in our condition, so diameter is 6 cm and thickness is 5. So if you thickness ratio, it will come almost like 50, more than 50 or 60. So we can use our ratio. So generally in cell model what we need to do is we need to take 3D geometry and extract surface, and we need to attach thickness to the surface, which represents the actual thickness of the geometry, and we need to do that. So here the condition is the reductive thickness ratio should be more than 5. So but we already have, so definitely this can be modeled shell using shell. Of course, using shell we can model, and using 3D we can do the analysis. So I have taken a snapshot of this model, actually I model 360 degrees to show the elements across thickness and selected on the sector model and represented here. So here we have taken 860 degrees and we have put nice thickness here, and we have put 3 elements across. So it is always advisable to have 3 elements across thickness so that the bending will be captured properly. And some other things related to boundary conditions. So in this case, the surface case is constant and axial direction. Axial direction in the sense so along this direction, we are constrained with that plan, and we have to go more circumferential direction. Circumferential means what we need to do is we need to rotate this node in cylindrical coordinates. Cylindrical coordinates are divided. our tangential to the. So here also we need to put a tangential constraint at 4 locations. So that will minimize the rigid body motion in that case. So on applying for applying load, we need to, as we discussed about series in RB3. So here we have created a RB3 on the, so we have put a constraint here and we need to apply moment here. So at this point, we have created a mass element, the center of the, you see here, same location. So at the center of the cylinder, at the forward plane, we have created a mass element and it is connected all the faces, forward faces, using arbitrary element function. So, and mass element is assigned with negligible mass and inertia. So if you take a cross section of this one, so this is the cross section and this is the mass element. So this is how Felix looks like. Arbitrary, sorry, arbitrary. So here mass element is the master node and all know on the forward plan. So if I take a cross section, so all nodes on this page are connected and connected to the master. So this is the master in the page. So this is how we connected here. So this is the master and this is the. So when I try to apply a moment and we applied um, moment 5/7 along with x direction. So along x direction in the sense on this push this way, this way. So this is our understanding, and when we try to see the result, it is giving in that fashion. Suppose if it is not giving similar fashion, then we need to understand that our simulation is appropriate or not. We need to understand what is the issue, whether our Stress variations to participate in cities. So stress can be very comparable competition can be very but it should not vary to throughout the city. So if you see this location, so the mental stress is very high, very high throughout the so if you see this location, stress is high here and gradually fading out. Then and quite opposite to this location, other way, that is this one, we are getting a control. So stress is varying from positive to negative through each decade. That is the reason. That is one of the reasons which this model was qualified for the accelerated analysis. Now let us look into closely the difference between arbitrary and theory for this particular problem. So, similar to theory, here also we need to create master from master nodes and nodes again on the parallel plan will be connected to the second. Carried out two iterations. One iteration we already discussed about theory. Second iteration we have created arbitrary and we want to see the difference between theory and arbitrary boundary conditions. So we see the method, we are getting two something here and here we are getting around 40 plus square. Around 40 plus.
NC plus.
This is RBC. So here it is 230 MPa and RB3 42 MPa. Now let us look at the deformation of what is happening here. So you can see here in RB3. So if you see here in RB3, the planets are flexible. See, there is a deflection happening across the system. If you take any picture, the planet is reflected. So particularly, you try to see here, the planets are with the group in the planet, the planet is reflected. There is no reflection here happening. So generally, planets at the top have more flexibility. So the reflection of land something like so here the planet is very low. So deformation. So when as it gradually deforms, the deformation of the control. So this is what happens here. So all complete plant is flexible here. The reason is we have used RBA3. But whereas here we have used series, we see here the deformation is completely uniform across uniform uniform. So this is the deformation. This is observed everywhere. And this complete plant is completely become visibility here. Whereas here it is completely visible. So same you can observe here. Normally it is if you see the you take a section here. So it is varying across the thickness, across the depth, whereas it is not varying. And it is perfectly visible. And it is completely flexible. And so you see the deformation because it is becoming very rigid. The deformation is also very low. And deformation is very low. So this simulates actual behavior on the case. Because generally planets want to rigid, they are very flexible. So this type of behavior cannot happen on the case. So this is the simulation. So series will artificially stick in the location where they are modeled. So this will stick in this location is completely different to the level of series. So this is used to model soft support whereas series are for the rigid support. So so basically whenever we try to do any analysis, we need to understand whether we need to apply RBC or whether we need to apply CE. So that understanding we should be having. So when we try to apply domain or courses, generally we prefer for RBC. Like if you want to apply domain from scale, usually we create RBC and we apply. We try to avoid most of the time. We'll try to avoid the maybe one more example is there. We can discuss on the basic difference are the Coming to same model, we discussed model can be modeled either shell model or 3D model. This model will also qualify for shell model because of radius thickness ratio is more than 5. So here the ratio is almost 50 to 60. So definitely this model qualified for the shell model. So here I will be explaining how to do shell model. Here typically what we do is we take a 3D model, whether if you want to do shell model, we do other couple of things. The model is complicated. We need to take characters support like immunography, Tegia. So these tools support is required to extract these structures. If our geometry is as simple as simple take we can take national water because we are comfortable, we can take it and we can model the structure of the geometry. So here what we have done is we have taken the cross section of the geometry, right? We extracted surface, so the outline to the surface. Basically we have used some bounding techniques and answers to extract the surface. So we extracted this surface here. So one of the important items is we have followed fillet here on the sharp bone here, and then we have extracted the surface. So on both sides we have followed fillet. So once surface is on, so what we do we need to extrude this line on the body, on the axis. So basically this is process done with the axis. We need to extrude this geometry with the double axis. So similarly we have done we have done the extrusion or heat. So then the cylinder then our this line will form a shell. So and then we have modeled this shell mesh using coordinated coordinates. So let us look at the cross section. So this is the cross section of the cross section, and this is the shell model, shell element. So you see here is once we have done the shell model, one of the important things is assigning real constant or thickness. So we see here thickness is varying. So here what we have done is like we are having a uniform thickness from here to here, and there is a thickness variation here to here, and there is a completely different thickness in this thickness given to this. So here we have assigned a thickness of branch thickness here up to this location, and this thickness is completely varying. So we have always we have done approximate value of this thickness we have given. So approximate value of this thickness we have given here, and here also we have given average thickness to this location, and this thickness we have given similarly. That side also we follow similar approach. So when you do this, you see here this geometry started as captured at this. So this is a very good understanding of how to model cell lines. So here the we could not able to model this type of machine. So that will result loss in thickness of the cable. So when you try to analyze this geometry, definitely the result will be coming more than the 3D model. The reason is, so for this type of analysis, this stiffness of this band will play major role. So we do not able to capture this rule. That is the reason we may have issues with the analysis. Because overall we may use some stiffness of this geometry. So I did not perform any analysis on this. Just to I want to give a understanding how to do a shell model. So this is what we need to approximate. And this also is getting approximated, not so accurate for this type of problem. So coming to similarities, I think we discussed about similarities in last session. Just I want to touch base on similarities. So similarities, as we discussed earlier, these are related to the artificial stresses caused on a geometry because of loads and application like application of loads and resolution. So if our mathematical problem or loads and boundary applications does not reflect to the physics of the problem, generally we get artificial stresses. The mainly these artificial stresses will occur whenever you apply a point load or point constraints in the one or two locations. So basically, why the similarities is caused is because generally a node is comprised of infinity. So generally, like stress is calculated load by area, and load is applied on a point. The area is very minimal. That will cause a infinite very high stress in the point. So these should be avoided using various techniques. Like instead of applying point load, generally we need to go at using couplings or constant equations. That is one way. Second thing is wherever possibility is there, you try to apply pressure loads. So either you can use couplings and constant equations, or you can use pressure loads. These are the two techniques you can follow. Let us take a simple example. A vertical bar subjected to point load. Here we have applied a point load here, and if you see, we get a very high singular stress with that load application. So definitely it needs to be resolved. This issue needs to be resolved because this is not correct, or this type of behavior will not happen in any of the mechanical model problems. So it has to be avoided. So one way of doing this model is simple way of doing this model is apply a uniform pressure on this space. That is one way. Second thing is we have RB3 and series concept. So that connections you can use, and so here what we have done is we have created a mass element at the center of this space, and we have connected all these nodes, all the case nodes to that mass element using one iteration we have used RB3 and another iteration we have used series. So here, when I try to apply arbitrary and series, if you see the deformation plots, so series seems to having maintenance. The reason is series will try to make complete location rigid and try to pull together. So whereas RB3 it will be like flexible. So it will try to pull based on the directions from the surrounding mass. So here this theory behavior seems to be reasonable compared to RB3. And when you check the stresses here, again we are getting very high stress at these locations in the RB3 connections. So when you try to unselect these locations, we are getting 25 kVs, 25 ampere. That is the actual calculated value, load by area. So whereas in theory, we got very high some high stress here, but after unselecting at the constraint location, so most of the location we are getting 25 kVs. So the complete this contour is varying close to 25 ampere. So this shows that seed is having correct deformation, um, the correct behavior when you try to pull complete geometry together. Means when you want to apply a uniform load on a face, then this approach can be used. Theory can be used. I don't know whether it is clear or not. Remember sometime back we discussed about applying loads on node. So I want to apply a load on this node. So one the group technique will be like suppose if I want to apply a load of P on all these nodes. So one way of applying is count the number of nodes. So 1, 2, 3, 4, 16. So P by 16 we need to apply on this nodes. So equal loads we need to apply on this space. So other way of this is very cool way because if I see this node, um, if I see this node, it is shared by only one element, and this node is shared by two elements. This node is shared by two elements. Similarly, these nodes are shared by four elements. This node is shared by four elements. So this whatever approach we will use on all nodes may not be correct because nodes are shared by multiple elements. So that is, I think we worked on this example, but I want to do that again so that will explain what the behavior of this example um, load distribution happening at the cross section using RBPI. So here, let us take this will take time because it is shared by one node. This is taking 2s, right? 2s, 2s, x. So I have four processes mentally. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total I have 32 is my work. So load distribution. So here we'll be having one-fourth load, half load, and the full load compared to 4 to 2 to 1. So this picture shows in RB3 load distribution is uniform in all nodes, and here load distribution is happening as per this thing. So here we are getting very less load here because it is shared by one node, and here we are getting better this load because it is shared by two nodes, and if you see here we are getting better than this node because it is shared by four nodes. So for this type of problems, typically we use series. So any questions on this example, on these two examples? If you have any questions, please raise. So that concludes our discussion on loads and boundary conditions. So on continuing on loads, so far we discussed on gravitational loads, and that is body loads, both gravitational and omega loads, and then point point loads, then surface loads, and another important thing is thermal loads. So basically, these thermal loads are very important when we try to do some analysis on aero engine components, automobile components. So because there will be a lot of thermal activity going on those components. So let us understand the basics of these thermal loads. So basically, whenever you apply any heat or if you are trying to cool, there will be always deformation happening in the components. Either it may be expanding or contracting, deformation will be happening. So to try to cool a component which doesn't have constant, let us take a component and we try to cool it to 1000 degrees, okay, and there is no constraints to this component, so it's really free to expand. And this expansion doesn't cause any stresses, but it will free to expand. Until unless if you arrest, there won't be any stresses happening in this component. So, so generally, like when there is a uh, thermal loads applied, if there is any restriction, then stresses will be induced. So apart from that, sometimes thermal stress is also induced due to non-uniform distribution in the atom. Suppose if you take this example, um, there are two components here. So and when they have heated here, so this is different material and this is different material. They will be having different coefficient of friction, coefficient of thermal expansion, that resulting in difference in the deformation. Since they are together, so and this red one is trying to flow more, and this is not growing that much faster than this one. definitely some deformation will be happening. So this will cause some stresses in the components. So one way is when there is a restriction, suppose if you take a this beam constrained at two ends, and when you try to hit it, it will try to deflect this one, and we will get a stresses because it's not allowed to grow freely. Similarly here, if they are having the same coefficient of thermal expansion, then if you try to heat it, they will grow together. But if there is any difference in the coefficient of thermal expansion, this type of behavior will happen, and it will induce stresses in the members. So to understand more on this thermal load, generally in finite element method, produced due to thermal field are computed for each element, and these are called as the initial stresses. Generally, what will happen whenever, suppose if I take a simple cantilever or something, and it is subjected to, say, thermal loads and as well as mechanical loads, first it will calculate initial stresses due to thermal load. It won't calculate stresses due to mechanical loads. And because of these things, so because of pressure, it will calculate initial stresses, and from initial stresses it will calculate nodal loads. So once the calculation is completed, these nodal loads are assembled, and the result is structures whose nodes have no displacement but are loaded by initial stresses. So basically, so still the calculation finite element method, there is a initial first step would be calculating the thermal loads from the applied thermals, and once the thermal loads are applied, that loads will be assembled into a matrix, and then we'll be already having a loads, but those for each node it will have no loads, but those nodes don't have any displacements. So then the model will be, the matrix will be solved for degrees of freedom of for each node. So basically, first step is it will calculate initial stresses due to temperature, then it will assemble into a matrix, model loads matrix. Then it will calculate the model degrees of freedom of complete global matrix, and then it will superimpose these stresses with the initial stresses. Then it will calculate the model degrees of freedom, then compute the element strains and stresses, and then it will superimpose these stresses with the initial stresses. Let us take a simple example. When cantilever is subjected to, say, this is T1 is a reference temperature, and T1 is a reference temperature. So, and then it is heated to T2, resulting there is an elongation. So then the thermal strain is nothing but alpha is the coefficient of thermal expansion into delta T. So delta T is nothing but T2 minus T. That is difference between the difference between the heated temperature to the initial temperature. So the initial temperature is also called as the reference temperature, and it will have a very important role in calculating the stress. Then the total strain is given by strain due to mechanical load and strain due to thermal. So here, let us say one minute. then once this is the total strain equation, that is strain due to mechanical load and strain due to thermal load. Then put together we can calculate this one from here we can get a stress due to mechanical loads. So other important things to be considered uh, while doing so far we have uh, analyzed only models which are subjected to mechanical loads. So for mechanical loads we typically give density and modulus and power. So when you try to solve a model for thermal loads, always we need to give in middle term this important thing is alpha quotient of thermal expansion. This is very much important. So while while performing a thermal status, while performing a analysis which contains thermal loads, it is always required to provide quotient of thermal expansion in the middle term, because the strain will be taken LR alpha delta. So this alpha is the thermometer. So this is very much required. And one of the important thing is we need to specify reference temperature. So this delta T is nothing but T applied. Delta T is nothing but T applied. Suppose let us just say I have just 500 degrees centigrade, right? And usually like analysts, most of the over the years, what we observed is most of the team members and our group will try to forget this value. Generally, we need to give this percentage. We need to give this percentage. So by default, in most of the tools, by default, this 30 will be default it will be 0. So if I were to give 0 temperature, then the both samples also will take 500, and there is a huge error because this delta T will feed into this calculating strains. This delta T will feed into here. That will be already having an error. So 500 versus 470. 470 is the actual value, but it will take a higher 500 degrees centigrade. So reference temperature will play major role in when there are thermal loads involved. And also one of the important considerations we need to take care is the differences in temperatures. Suppose if I take a one component, let us take a rope. So hot air will be coming. Right? So this will be very hot air. As it goes down, it will be a little bit cooler. And as it goes up, it will be a hotter. So here food, here hot. Okay, on single component. So there will be thermal variation. So this variation towards the component will also cause thermal stresses. So it is very important for us to understand these thermal loads are one of the primary drivers for the mechanical components. If they involve if they work in a thermal environment like automobiles and aero engines, they work on thermal environment. So thermals are primary drivers. Mechanical loads are secondary drivers. So I will provide some more insight to the thermal loads in the next session. So this concludes today's session. So just I would like to know if you have any questions. So we can initiate interactive session here. So any college would like to have interaction to discuss any questions. JNTU Vijayanagaram, any questions? I switched on interaction now. So any questions, please raise. JNTU, I think. I think there is a question from Venkateshwara College. Please provide model question papers. So I'm not sure like who will be providing question papers, but yeah, I'll check with your coordinator as well as our learning and development team at SIGN to see whether we can give some question papers. But at present, I don't have any in my hand. But let me check it out with our L&D team. Any other technical questions? Please let me know. Any doubts? And I have released at least 7 to 8 PowerPoint files out to our L&D team. So very shortly we'll be getting all the files. So I have given only 5 files to you. Remaining 8 to 9 files will be provided by L&D team very shortly, and you will be receiving all those files. So there is a question from JNTU Vijayanagaram campus: how master node is created in case of Francis creating an area? How master node is created in case of Francis creating area? I think there is a question from JNTU Vijayanagaram. What they are asking is how to create a master node in ANSYS. For example, what we have discussed. So let us take a in the interface, whatever phase we have used, and we need to create a sensor one key point. Or as I told, another method is usually the ANSYS circuit is formed by water. So you can join these two points and you can divide and you can get a key point here. This key point you can select mass 21 element, mass 21 element, ANSYS, and you can mesh this key point. Generally we can mesh volumes, we can mesh areas, we can mesh lines, and we can mesh key points. So volumes can be measured with volume elements, area is measured with shell or plane elements, line is measured with beam elements, key points are measured with modulus. So we can measure mass 21 elements. So mass 21 elements will be created on this point. Then we need to assign real components. Go to real components. If you will be asking just mass in x direction, mass in y direction, mass in z direction, and also inertia in x direction, inertia in y direction, inertia in z direction. You can say maybe normal value 0.001. So that won't have any impact. So this is how we need to create mass elements. So basically, if you are able to create a key point, then we can measure it, or you can directly create a node. So if you get a location here, if you find out the location, so we can use create node option. Then we can put the location values, and then we can assign we can set element on node. Create element on node. That option is there in answer. We can use those options. Hope I cleared your question. If you have any question, please wait. Any other questions? JNTU Vijayanagaram, your question is clear. Answer is clear here. And can you switch on interaction mode so that I can interact with you? Yeah, now you can interact with me. So, hello, JNTU Vijayanagaram.
Sir, after creating a area solid annulus, if I create a key point at the center of the annulus, and if I apply constraints, then it is applicable to whole means whole solid body, sir. I mean, after creating a solid annulus and selecting its center and creating a node.
I'm not able to hear you.
Sir?
So basically, to understand whatever I explained, right, you should be well versed with ANSYS tool. Okay, until unless if you are not good enough. No, I'm not able to hear you. Maybe check your like audio system. Or you can type it otherwise. So whatever I explained is like if you are well versed with ANSYS, then it will be very easy to understand. So basically, I'm still not able to listen you. Just maybe you can check it out. But what I mean to say is, you can create a key point at the center of the circle. That is very easy. Maybe you can join the two. If you draw a circle in ANSYS, it will be formed by four arcs here, which are 90 degrees apart. So you can join the two lines like this, and center you can divide that line and you can get the center. That is one of the easiest way. Then you can mesh that key point. So that is one way. Otherwise, if you know the locations, you can create a key point, or you can create a node. If you create a key point, you can mesh that key point using selecting the mass element. Or if you create a node, you can create an element on that node. These are the two options. Maybe the Kansas manual is an excellent manual. So you can refer those manual how to create a mass element or how to create elements. You can follow the simple steps. So any other questions? Vijayanaram, your question is clarified. Maybe you can try one example on after this class. If you are still facing problem, maybe we can I'll explain further maybe in next session. Yeah, you try one example and let me know in next class. Then I'll try to clarify if you have further questions. Any other questions? Okay, if you don't have any questions, then we'll meet again on Tuesday and we'll discuss more on thermal loads, and then we'll look into the nonlinear analysis. And have a nice week ahead and weekend. And we'll meet again on Tuesday. Thank you.